All right, good afternoon, everyone. I'm Hongyu. Today we'll be talking about week 5's exercises. Specifically, I would like to focus on three main topics. First, I will jog your memory a bit on HBase and HFile's organization by going through some example questions in this problem set. Secondly, we will move on to Bloom filters, which are arguably one of the most important topics in computer science, because they are really applied everywhere in memory technologies, in databases, you name it. And specifically, we will be focusing on deriving and understanding how we can calculate the false positive rate, not only how we can use it, but also really understand how it works. And lastly, we will also touch upon log structured merge trees, and they are really an essential component that is the bedrock of NoSQL technologies, and it's one of the main reasons why NoSQL even works in the first place. So lots of exciting stuff. Let's get started. First of all, it's a bit small. Let me zoom in. So first, I would highly recommend going through this problem and interacting with HBase from command line with wiki small dataset. And specifically, you should get yourself familiar with, for example, the single column value filter, how to use it, how to combine multiple single column value filters, and how to scan the table, right? How to provide keys, role prefix filters, for example. So you should be aware of the kind of output they provide, and to get yourself familiar with the syntax, because you're expected to write queries very efficiently during the exam. So that's the first part, and I've got lots of complaints regarding the Docker deployment we provided on Mac, Apple Silicon, but I'm sorry, I have no solutions for that, because the Docker environment is emulated on Apple Silicon and it's pretty slow. Sorry about that, but give it a try and maybe subsample the dataset a little bit. So sorry about that. Secondly, I will be, the screen frozen, right. I will be talking about the physical storage of HBase, right? This is really the core of how HBase stores its files and key value pairs, right? So here we have a view of a table, as we always have, and for a table we have rows, we have columns, because HBase is a NoSQL database, right? So to perform more efficient read column-wide, we separate the columns into so-called column families, right? Potentially we have lots of other column families as well, and then we partition the rows into regions, right? So this is one of the reasons why I can conduct range partition and range read, right? So in this case, we have a region ID for this region and several rows. These rows are combined to another region and so on. And for each row, we have a unique row ID, right? This is the primary key, if you like, that identifies this row, but not this cell, right? We will talk about that later. And for each column, we also have the column qualifiers, right? So this one is column 1, column 2, and together the column quantifier with the column family and the row ID will identify a cell, which is a key value pair, and the conjunction of a region and a column family is the so-called store. Okay, a store is basically, the intersection of the region and a column family. Okay, they are stored together and read together as well. And so how they are stored is basically they are serialized in this manner, right, and into a so-called HFile, right? To keep in mind is that so we can create, so for example for this role X, a specific column family only for this role, right? What that means is that for the rest of the rows, this column would be empty, right? This is totally fine because in HBase, in a NoSQL database, this is only a logical view, right? Keep that in mind. So what we will do when we are writing to disk is that we will just serialize the existing values, right, and skip the non-existing ones. Right, so keep in mind this is only the logical view, right, from 1,000 miles away, from the user's point of view. And the H files will have is the row IDs, right, the column family, and the version, right. So these three uniquely identify a value, right, and the last column will also have the value stored. And the H files are split into different so-called H blocks. Each H block is typically a size of 64 kilobytes, if I can recall correctly. But this is not fixed because H block is also totally logical, right? There's nothing physical on disk that's called H block, right? H block, the sole purpose of H block is to facilitate the indexing of H files. So by having multiple H blocks, we are better indexed. We are better indexed into different locations of H file, which we will see later. Okay. Any questions? Everything clear so far? All right. Okay. Good. Next, we will move on to the HBase architecture. So hopefully this view is not unfamiliar to you, right? This is very similar to what we've studied with HDFS, right? Because HBase is basically built on top of HDFS. So what we have here, let's see, we have, as we've discussed, we have the tables, right? Oops. We have the table, and the table are range partitioned into different regions, right? In this case, we have different regions, and these are the range partitions. Okay, and then different rows were grouped into different regions and sent out to the region servers here. Okay, and these servers, these region servers have direct access to HDFS. Right. One thing I'd like to draw attention to is that each region server has full access to HDFS, right? Each of them is a client to HDFS, so they can access the full server as an HDFS client does. Okay, and this I hope you can recall what we've discussed a few weeks before when we were introducing HDFS and the benefits of co-locating a client with a data node process, right? In that case, we will have a local copy of the file we are writing, so we don't actually need to, go through all the protocols of HDFS, and we can access the local copy very efficiently from the region server itself, right? It's just a IPC, an inter-process communication, and you get the data back because the data is co-located with the region server. So this is pretty efficient, okay? Right. Any questions at this point? Yeah. Question? Right. Okay. So the question is, what do those colors represent? Yeah, so to quickly go back, so these colors, for example, the red, the purple, the red, so these are the region IDs. They are different regions, right? So for example, this is the green region, this is the red region, and so on. So we are grouping multiple roles together into a region, and we sending each of those regions to a region server. So each region server is in charge of different partitions of the table. Does that answer your question? All right, yeah, great. Yeah, so this HBase, by the way, isn't really what it was built based on Bigtable, right, from Google. Bigtable, well, technically plus Google file system, right? So they are basically doing exactly the same thing, right? But technically Google file systems has been updated to clauses. If you're interested, take a look at it. But yeah, basically they are along the same vein. All right. Okay. If there's no more question, then we move on. So that's the architecture of HBase and the physical storage of HBase as well. So what I'd like to quickly go through is task 3.1. So what we have is the format of the HBase keys, right? So we have the row length preceded with a row key because we need to know the length of the row, right? This is basically the prefix encoding. And so in this exercise, we're simplifying several stuff. First, we only have one column family, right? So we don't care about the column family. Yeah, so maybe it's easier to look at this example, right? So here we have the HFile. The first part, this part would be the H block ID, right? And this part is the row ID. This is the column qualifiers. This is the timestamp. These are the values stored in the H file. And for when we're looking at the H file indices, what we have is the same except for the last column. These are the block indices, right? So for example, in this case, this is block 1 of HFile 1, block 2 of HFile 1, and so on and so forth. All right? So what we are supposed to do is to, so if we're looking at the questions, what we are doing is to get the latest version for each of the queries, right? So if we have many duplicated values for the same key, well, we are supposed to return the latest version. And this is not always the case, right? So it really depends on the kind of requirements of your queries, right? So if you were to, for example, sometimes you have the requirement of time traveling, meaning that the user requires multiple versions, and maybe he or she wants to revert to a prior version, right? Stuff like that. This is quite similar to the functionalities provided by relational databases like the Oracle databases. But yeah, that's an FYI. So I will not go through all the queries. I will just focus on the last two ones, which I find quite interesting as an example to show you how you can do it. So first, I'd like to ask you how we can find the value, right? So as I said, HBase is a NoSQL database, right? Unlike relational databases, we have an index that tells us where the data sits. And in a NoSQL database in HBase, we really have no idea where exactly the key value pair we are looking at sits, right? So in order to find where the key value pair resides, how can we do that? How can we do this navigation? Any ideas? Right. Exactly. Exactly. So everywhere, right? So we need to literally look at everywhere, right? So we need to first go to the mem store, right? We check the mem store is like the first line of cache that caches the latest data. And then we go through the HFile indices. From the HFile indices, we go to every single HFile we have on the disk to search for the key value more efficiently. But anyhow, we need to go through every single location to find out the desired data location. And we will talk about, well, you would say this looks like extremely inefficient, right? And how can this even work? And we will talk about the kind of the tricks and special data structures that make this possible, okay? But first, the first key we're looking at is 640, right? First, we're looking for 640. The first place we're looking at is our mem store. Do we have 640 in our mem store? Yes, we do. We have the column C in our mem store, and then we go to the HFile indices, right? So this tells us the starting position of each block, right? So in this case, the first block starts, the starting index is 109. The second block, the starting point is 400, and so on. So then we know that for 640 is exactly in this block, right? So we should go to the go to HFile 1 and to look at the third H block, right? And then for the second H file, we can see it's between the range of 399 and 576, right? So this is the minimum value, and this is the maximum value. And for the third block, what we should look at is for a 6 is the last 3 blocks, right? So the minimum is 489 and the maximum is 809. All right. Okay, so what do we do? Sorry, I was wrong. We should look at this position, right? So these 2 blocks. So first we go to HFile 1, right? HFile 1, what we have, we check if we have 640. We have actually 2 rows, right? We have our column A and column C. And then we go to HFile 2 to look at the block 3, and we found no 640. And then we go to HFile 3. We were looking at HFile 2. Now we are looking at HFile 3. So do we have 640 in HFile 3? No, right? So then what we do is that we can write down the results directly. So the results would be, first we're looking for column A, right? The column A, we only have 1 value, so there's no ambiguity, right? So we just write down 640, column A, the timestamp is 5, value is long, and where it came from HFile 1, right? And then we look for the column B. Well, actually, I was wrong. Sorry, the column B was in HFile 2, right? So we write down the value 640 column B, and the timestamp is 6. The value is live, and it comes from HFile 2, right? Next, if we're looking at the column C, we'll find that, well, we have both it at in the mem store and in the HFile. By comparing their timestamp, we see that, well, the latest version is the mem store version, which is not surprising because it's caching the most recent version typically. So you just write down still the row, the column, the latest timestamp, the latest value. Is that right? Yes. And this comes from the mem store. Okay? Does that make sense? Any questions? Yeah. Go on. Right. Right. Well, you're right. So the question is why didn't I look into the gray H blocks in HFile 2 and HFile 3? Yeah, that's because I made a mistake, right? You're right. So I don't need to look into the gray blocks because this is the mean value, right? And this is the max value, so of that range, meaning that the minimal value in this block is 576, and the maximum excluded maximum is 767. So if I were to look for 640, I don't need to go into the gray blocks. This applies here as well. So I only need to look at the green H block in both HFile 2 and HFile 3. Thanks for pointing it out. Yeah. All right. So next, we'll move on to the last query, right? The fifth query. So what the key we're looking at is 443, right? So now we're looking at, 443. I need to plug in my charger because my iPad is dying. 1 second. Right. So next, right. Okay, come on. Yes. So next we're looking at 443, right? So first we go to the mem store. Do we have 443? No, I don't think so. We don't have the row ID 443. And then we check the indices. So 443 lies into the yellow block in HFile 1, also the yellow block in HFile 2, as well as the last yellow block in HFile 3. But we don't have any 443, meaning that after we have gone through all the traversing for all the components from the memory and on disk, we were basically chasing a ghost target, right? We are, traversing all the storage elements for a non-existing key value pair, right? And this is extremely expensive, right? And that's really motivated why we need a data structure like Bloom filter to help us filter out those non-existing keys before we traverse to the deepest level of our storage. Yeah, question. Right. Right. So the question is, where are those HFile indices stored? Okay. So in the lecture, Jason has said, the indices were stored at the beginning of every HFile as the metadata, right? So you know that the ranges and you can access it very easily. So that's for this course. Honestly, I don't agree. I think from the papers and the technical document, I think the HFile indices are stored in mainly in memory. But yeah, but for this course, they are basically the header metadata of each HFile, and those HFiles are nothing but real files stored as HDFS files. Okay. Right. Question. Yeah, go ahead. All right. So the question is, if we have the index into those H files, can we access directly to that key value pair? Can we jump to that key value pair very efficiently? Well, so the answer is yes and no. Yes, you can technically, once you've got the index, for example, in this case, we have the index, we know that the key value pair is we're looking at, for example, for 3 is in the yellow box, right? So of HFile 1, then we can directly move to this block. But the thing is to keep in mind, these H files are nothing but they will be stored as the normal files on disk, right? Meaning that if you were to access this file, how you can do it, for example, in C, you need to do a file seek, right? For example, like this. You need to do a file seek to really get to that location. So although you can have what you can do is that you can provide an offset directly, right? So at the beginning of the file, you move the cursor directly by this distance, this offset, right, to that block. But once you are at this location, you still need to do the scanning, right? This is not the random access. So that's the no part, right? But that's a good question. Yeah. So these H files are nothing but the system files stored as the HDFS files. Okay. Alrighty. So another question. Right. So the question is, if I understood correctly, the question is, why do we have these red regions spread in different H files instead of stored together, right? Is that right? Okay. So these colors are only assigned after the blocks are stored. So they don't have any semantic meanings already, although these blocks are all in red, semantically they don't have any relationship. So the sole reason why they are all in red is because they are all located in the first block of their corresponding H files, right? So yeah. Right. Right. So yeah, that's exactly what's happening. So just to quickly reiterate, what he's saying is that is that because these files are written in sequentially? For example, we're storing key value pairs, and only we after filling up the first H file, can we move on to the second one, and so on. And the older the file, right? The older the file, the later we write to a file, the older the age of a file. That's exactly what's happening, right? So we're first filling up the first file, and then we move on to the second file. So the colors are only assigned once those key value pairs are stored. Okay, that's a good point. Thanks for asking. Right, so quickly move on. So what we've talked about is that, we found a really ghost target, right? This guy is really bad because after going through all our storage elements, we found it's not there, right? And this really motivates why we need a data structure called Bloom filters, right? So what a Bloom filter is basically a bitmap, right? So in this case, we have n entries in our bitmap, and each entry is either 0 or 1, right? And then we have a set of functions. We have h1 to h2 and h to hk. So we have k functions, right? So we have n entries, we have k functions, and each function is setting some bits to 1 for a single item, right? H2 is setting some bits to 1 for a single item, and we assume that the Bloom filter has already had m items inserted, right? Any questions? All right, so I have a question for you. Why do we need more than one hash function? Any ideas? Why do we need? Why don't we just use one hash function? Yeah, go ahead. Right. Right, exactly. You mean collision rate, right? Exactly. So this is because, say, for example, if we have a hash function having a collision rate being 50%, right? This is exceptionally high, right? So we wouldn't have this kind of garbage hash function in real life. But say we have a hash function with a collision rate being 50%, right? So what we can do is that we can just, if we were to have k equals to 10, meaning that we have 10 hash functions, right? The collision rate will be what? Will be rho to the power of 10, right? Which is smaller than 0.1%, right? So by having this k as a knob, we can drive the rho down efficiently and exponentially. Right? Because this is a compound probability event, right? If we were to have only one function with a collision rate of 50%, and the only thing we need to do is to stack 10 such hash functions, and immediately we'll get a collision rate below 0.1%, which is quite dramatic. Question? Yeah. Right. So the question is whether these functions are applied in a round-robin manner, if I'm understanding you correctly. Yeah. So no, they are not. So maybe I should have introduced this in a bit more detail. So what we are doing is that, say, if we have an item x, right? So the way we insert x into our Bloom filter is that we iteratively apply all the hash functions we have. Say if we have if we have two hash functions, then what we do is that we first apply the hash function 1, right? And then we set some bits, right? Say the hash function 1 sets this bit, and this bit, right? And then we apply hash function 2, and this function would set this bit, and this bit, right? And you might ask, well, what does this buy us? The reason why we are applying two hash functions is because, as I've said, so if you are querying x, right? So you are checking if x is in our key value store or not. You can just check all the entries, the hash function, the results of the hash function, right? We can check, well, this function, this bit is set, this bit, all the bits of it has been have been set. Then this means that the item x is probably in our filter, right? So what this is telling us is not whether this x item is in the our filter or not. What it can tell us is that it's probably in our filter, right? And and if you have an item y comes along and we hash it with the two hash functions, then what we will have is that, well, the only thing that's preventing us from making the mistake that y is in our filter is that as long as there is only a single bit, right? For example, all the bits are set, right? This bit are all set, but this bit is a 0, right? So the hash function 2 is giving a 0 on y. Then we are 100% sure that y is not in our Bloom filter. Okay, that means that we Bloom filter can have false positive rate, right? So the false positive rate of Bloom filter is greater than or equal to 0, meaning that if Bloom filter says the item x is in our filter, then that's probably wrong. That can be wrong. But if the Bloom filter says, well, y is not in our has not been inserted, then we're 100% sure that y is not there. So we have no false negative. So the false negative rate is 0% always. And we will look at it, how to calculate the false positive rate. Does that make sense? Right. And so next, I will be focusing on, how we can calculate the false positive rate, and also how we can simplify the formula derived from 1 using E, so the Euler number. And finally, I will talk about how we can choose K when M and N are fixed. Okay? Any further questions at this point? No? Alrighty. So first, I'd like to ask, what is the probability of a bit being 0 after M items have been inserted into our Bloom filter? Keep in mind that we have K hash functions, right? We have N entries. Okay, and we have M items inserted already. Okay, using you're supposed to express this probability using these three parameters. Any ideas? Any takers? Well, maybe let me ask a simpler question. What is the probability of a single bit being set by one hash function? Yeah, go ahead. What? Right. So by perfect, you mean the hash function is uniform, right? and 50%, I assume you mean 1 over n, right? So because you said like the hash function is perfect, assuming the hash function is perfect, then the distribution of the hash function, well, what the result of the hash function should be uniformly distributed along the real line, right? So in that case, if we were to have n entries in our hash set, so the probability of one bit being set is is 1 over n, right? So then the probability of a bit not being set, a bit being set to 1, not being set to 1, would be 1 minus this one, right? So this would be the probability of one bit not being set to 1, right? But this is only like a single hash, a single time. We have, remember we have m item already, and we have k hash functions, right? Meaning that for each item, we'll repeatedly apply k hash functions, right? And not repeated, we'll sequentially apply k hash functions, meaning that there are k times n, k times m, chances that this bit could have been set to 1, right? So this is the total, the total number of times a bit could have been set to 1, right? So this is the total number of times. So we have k times m, right? This total number of chances this bit could have been set to 1, right? And we take the exponential of it because this is really a compound probability event, right? And we call this value p0, right? And then what we have also is another value called p1, and this is what? This is 1 minus p0. It's the opposite of p0, right? What this tells us is that this is the probability of one bit being set to 1 by any of the k hash functions. Okay? Any questions? Nope. So then we will move on to answering the question of the probability of a false positive case. And what this is asking is the equivalent of what? Of asking what's the probability of all k hash functions set a bit to 1, right? This is where we are talking about the collision, right? So all k hash functions are hashing to the same value, right? They are making the same, they are colliding with each other, right? This is the probability of k hash functions happen to hash to the same slot, right? What would be this value? Any ideas? this is nothing but the P1 to the power of K, right? So remember what I was talking about. P1 is any of the K hash functions setting a bit to 1, the probability of any of the K hash functions setting a bit to 1. And the false positive case is where all of the K hash functions setting the same bit to 1 at the same time. They're colliding, right? So we're calculating the probability of K hash functions colliding with each other, right? And what this translates to is, is 1 minus P0 to the power of K, right? Which is 1 minus 1 over n to the m times K to the power of K, right? Well, this is a bit a monstrous formula to look at. And indeed, we should simplify this a little bit, right? Because like the K is both outside and inside the bracket, and one is driving up the false positive rate, one is driving down the false positive rate, right? So that's why we want to next simplify this expression a little bit. Okay? Any questions at this point? Yeah, go ahead. Right. So the question is, can we have, so I think, yeah, the question relates to back to this picture. Can we have, separate hash maps for each of the function? A separate hash map for each of the function, right? Technically, yes. That's a yes. So we can have a separate hash map for each of the hash functions we are having for our Bloom filter. But it's a waste of space because basically when you join all of the K hash maps together, they are basically having the same effect. So that's why we're merging these K hash maps into one. So in that case, when hash function X hash to a slot where the slot has already been set to 1, it does nothing. Okay, does that make sense? Great. Okay, right. Yeah, question. Right. So the question is, can we set one bit? Can a hash function set a bit to 0? No. So the hash function, the only thing the hash function does is to set a 0 bit to 1. Okay. All right. Thanks for the questions. Moving on. So what I would like to do is to simplify this monstrous formula, starting with the core, especially this part, right? I want to, what I want to do is to simplify this to something with the base of e to the exponent of something, right? Typically how we do this, kind of a simplification. Any ideas? Yes, taking the logarithm, right? So what we do is that we just take the logarithm, right? This is the equivalent of the original expression, right? And what this gives me is that I can extract out the mk part in front, and we will have the ln 1 over n, right? And this should ring a bell to you guys, right? From undergrad, how we simplify this kind of formula, right? So this is similar to the format of 1 plus x, right? And we can simplify, how we can simplify this form? Yes, Taylor expansion, right. So, so this is the case where we have x being minus 1 over n, right? And what we can do is that we can approximate this part using Taylor expansion, right? So specifically, what this means is that we can have x being x squared over 2 minus, no, sorry, I think it's a plus, sorry, 3 over this minus x to the power 4 over 5. And so on and so forth, right? And yeah, this is also called the Mercator theory, if you can recall. Right? And so before simplifying, in order to simplify this, we should look at the quantity of this entity of x, right? It's, specifically, we should look at n. So typically for a hash set in a Bloom filter, at least we will have, well, a decent size would be 1,000, right? Say 1,000. So this means that we have 1K entries in our hash set, right? Hash map. And then what this translates to is that, so if we substitute the n in, what we will get, let me see, yes, we will have minus 1 over 1k minus, if we substitute this in, will be 1 over 2 million, right? And then we have a minus 1 over 3 billion, and so on and so forth, right? So as you can see, these values are already very small, right? So what do? We ignore it, right? Yeah, exactly. So we just skip these values, right? So what we are doing is that we're approximating ln 1 plus x with x directly. So what this tells us is that, well, we're approximating, ln 1 minus 1 over n with 1 over n directly, right? So if we substitute this in to this expression, what we have is that this is, this is approximately e to the minus 1 over n times mk, right? And what this gives us is that the probability of the false positive rate, the false positive rate can be simplified to approximately 1 minus e to the mk divided by n raised to the power of k. Right? Does that make sense? Any questions? Nope. Good. Everyone on the same page? Right. Okay. Moving on. So what we have now is that, well, I just rewrite this function here, this formula here in a slightly different form. So what we want to do is that, well, it would be nice to extract this term out, right? So this is sometimes called the number of items per slot in our hash table, okay? And if we want to, optimize for k, then for now we will just keep this item constant, right? We are fixing this term for now, and we are optimized for k. Okay, so in this case, I wanted to ask, what if we have too many hash functions? For example, we have a very large k. We have as many hash functions as we have the number of slots in our hash map. What would it happen? Yeah. Exactly. So this term P1, this will go this will become very small, right? So what we will have is that we'll have a P1, we'll have a value approximately to 1 raised to a large k. So when I raise a number approximate close to 1 to very large k, regardless of how large the k is, we'll still have a very high false positive rate, right? Making sense? Okay. What if we have very few hash functions, right? Say I only have one hash function. What would this do? Sorry, this is the P1. Yes. So what this means is that, well, we are raising, change the color. We are raising the P1 to a very small number, right? We can even ignore it. So this gives no exponential effect that we previously mentioned, right? We can't drive down the collision rate exponentially anymore, right? So this will also give us a very large false positive rate. Okay, so what this tells us is that, well, if we put this on a 2D grid, what we have, to the coordinate, if we have a k on the x-axis and the false positive rate on the y-axis, what we have, we would approximately have something like this, right? On the one side, we have the first case. On the left side, we have the second case. And at the lower point, we have something called a sweet spot, right? This is where we find the optimal k value, right? How do we find it? Taking the derivative. Yes, exactly. So given the time, I will not do it here, but basically, so how do we deal with this kind of derivative? Yes, taking the log first. So basically, so first you take the log before you take the derivative, calculate the derivative. But basically, the derivative of the false positive rate, the false positive formula with respect to k, we set it to 0, and this gives the k star being ln to, let me check the answer, terms n over n, right? And this term is sometimes called the bits per item. Okay? Any questions at this point? Yeah, question. Right. All right. So the question is, why having too many functions is a bad thing, right? Why having too many hash functions will have a high false positive rate? Well, there are two parts, right? First, does the mathematical reasoning make sense? So if we were to have k very large, then p1 would be approximately to 1, and yeah, we will have a very high positive rate. Okay, then intuitively, what you can think of it, so say, let's give a very concrete example, right? So if we have a hash function f1 with a hash map here, and so this we hash x, and this gives the this sets 2 bits, right? And then we apply the second hash function here, and then this sets different bits, right? So basically, each hash function will have different outputs for different for the same value we're looking at, right? So if you were to say, I'm only having n entries, right? And I'm only having n entries, and you are and I'm only have k, but k is equal to 2. So in this case, we are already having too many hash functions with respect to the n entry we are having. And you can see when we are merging these two bitmap together, we'll have a very cluttered. I can do better than that. We'll have a very cluttered hash map already, right? So it's very, so this is this gets back to your previous question. This is why, you know, for example, another value comes along. It's very unlikely that it's very likely that this will indicate this kind of value hash map state will indicate why is in the hash map, right? This would be a false positive rate. So we will intuitively, you can think of it as a very clustered hash map state when you are having too many hash functions. Okay, and this is also ties back to the design principle of Bloom filters, right? So basically, in Bloom filters, we're having the number of entries way smaller than the number of files or the items we have, right? So you really need to design the n and k very carefully. Okay. Does that answer your question? Okay. Okay. Great. So that said, another point, just FYI, so now we're optimizing for k, right? So we can also do the same thing. We're fixing k. For example, we're fixing k to the optimal value k star, and we can also choose the best configuration for m and n, right? And you can also derive that, and basically the result would be, so the result would be, let me think, yes. So the result would be, this would be 2. So meaning that the bits per item would be 2. So the state where the Bloom filter is most informative is where we have half of our slots being occupied. That is where, yeah, the Bloom filter can really give us the most information. Okay, but that's just an FYI. If you're interested, please look at it. Yeah, that's basically how we derive and understand the formula. So in the exam, now hopefully you can not only use it, but also understand what this formula is telling you. All right. Okay, moving on. So yeah, so this part I recommend reading through it. So this is basically what we were talking about. We have, in this case, the item being the name, and then we are pushing the item through multiple hash functions, and each hash function will set some bits in the hash set, okay, our hash map. Right, so just to quickly demonstrate how you can do this kind of exercises, this would be one of the simpler ones you would get in exam. But basically, so what you get is that you will have a hash map you can work with, and then you will have a list of values, and what you are supposed to do is to calculate the hash value for each of the item, and then you set the hash map accordingly, right? I will just do a few of them as an example. So first we are looking, so what are the hash functions? The hash functions are the simplest and maybe the simplest hash functions you can get. So hash 1 basically is taking the first letter of the string. Hash 2 is taking the second letter. Hash function 3 is taking the third letter, and so on, right? So what do we have for round? For example, we will have round hash function value all u, right? And for word, we will have as w o. For pass, we'll have p a s, right? And then we just set the bits accordingly, right? So what we do is that we set, for example, in this case, ROU, ROU, right? So the highlighted items are being set to 1, SWO, SWO has been set. As I said, if this bit has been set, we do nothing, okay? And then we have PAS, so we have PAS. Where is S? Yeah, S being set, right? So this basically are corresponding to 1 bit at the top, right? And then what we have is that, well, these are the items inserted in the Bloom filter, and these are the queries, right? So we're trying to find out whether, for example, the word sword is in our has been inserted into our Bloom filter or not, right? So in this case, what we do is that we calculate the hash values again. So this is really a toy example, right? And what we do is that we check if all of the whether all of the values have been set, the corresponding bits has been set in our set, right? So SWO, whether it's been set, so we check SW, right? So they have all been set. So what we have is that in this case, this is a yes, right? And whether this, and we check the item, actually this value has been inserted. So this is what? This is a true positive, right? And then we check the word sound. So we produce the hash values, right? SWU, and we check again. So we check S being set, U being set, O being set, right? So the Bloom filter will say, yes, this value is probably has probably been inserted into our Bloom filter, right? So what we do is that, but is that true? No, right? So there's no such word being sound, right, inserted into our filter. So this is what? This is a false positive. That is where we have a collision, right? This is actually a collision. But as I said, these are the most stupid hash functions you can get under the sun. But yeah, so I think you've got the ideas, right? Okay, then try the rest yourself and to just get a hand of it, why it works. And one thing I'd like to mention is that the last question, right? Which of the words that are flagged by the Bloom filter as not belonging to the set actually do belong to the set, which is asking the false negative rate, right? So this is asking the false negative rate of Bloom filter. What is it? Yes, no, right? So never, ever right? So the false negative, the probability of a Bloom filter giving a false negative case is 0. Okay, this is really the crux of a Bloom filter. Okay, I hope that is obvious to everyone. Right, so the last bit would be task 3.3. Would like to quickly go through. So this is building an index. As I've mentioned, an H block is typically 64 kilobytes. And for this exercise, we are assuming that we're only, for each H block, we're having 4 bytes, right? So what I want to highlight here is that, so when we're building the index, what we do is that we're chunking H files to different H blocks, right? So in this case, we're counting, and what I want to draw attention to is that the block size can actually exceed the 40 bytes limit, right? So in fact, if the last block were be to say, if the last block were be to 100 megabytes, right? This can be well over the 40 megabytes limit. But that doesn't matter because those H blocks I've mentioned are logical structure, right? So they are just there to serve the purpose of indexing the H file, right? And one thing is that the minimum range indicated here, this is inclusive, right? So this is the inclusive maximum, minimum, but the maximum of this block, right, is exclusive, right? So the maximum is outside of the first red H block. Okay, and another one you should notice is that the last H block can be smaller, right? This can be smaller than 40 bytes that we set, right? Other blocks have to be greater than or equal to 40 bytes that we set. Okay, hopefully that that clears things up. No questions? Okay, so then exercise 4. For the sake of time, I will move on to exercise 5 just to look at it, to think about how we choose the most efficient row ID, right? So that's the primary key in this key value store, HBase. What I am going to talk about is the LSM tree. So it's pretty important. Although it's optional, I think it's very important to have an idea how it works and why this really makes HBase efficient, right? So LSM tree is really the backbone of NoSQL database, right? This is really the backbone of NoSQL. So if you can recall, in the SQL relational database, what we have to index our tables, we have B trees, right? We have B trees or B plus trees, right? So where we have root nodes, and each root node has lots of children nodes, and then each of the children node would have lots of leaf nodes and so on, right? And this is really optimized for reads, right? This is read bound. So because we want to have fast read, so on the positive note, this data structure gives us really fast, low latency in reads, right? But The downside is that when we are traversing down the tree, this really causes lots of random access, right? So if we're traversing down the tree, this really causes lots of random access. So this and random access is a key enemy in I/O operations, right? So this really makes the B trees we're talking about in traditional relational databases really bad at injecting data. Right? If we have a huge amount of data to inject, and this will kill our performance immediately, right? So what like the log structured merge tree does is that we have first an in-memory tree, right? So what we do is that we are keeping all the key values sorted, right? And then what we do is that we're periodically flashing to disk, right, to different a smaller tree, and we are merging smaller trees into bigger trees, because when we are searching for key value, we don't want to have a million tree roots. We want to limit the number of trees we are looking at, so that we can search for at the top level as efficiently as possible. Okay, I will next go through a series of slides to demonstrate this process. Okay, so what we initially have is that we have a I hope this is visible to you. Is it? Okay, right. So what we have is that we have a client talking to HBase, right? And the first thing, maybe we want to write a value, right? We want to write C1. So C is the key, 1 is the value, right? And the T1 here is the timestamp, right? So we're inserting a value into HBase. What HBase will do is first using its DRAM to cache the value in memory. So in the mem store, right? And then we're inserting the second value, and then we are inserting the third value. And notice that those values are sorted by the key, right? So A, B, C, they are sorted by the key when they when they were inserted, right? And here we're making an assumption that our mem store has the capacity of 3, right? So this is one of the conditions that dictates when to flash to disk, right? Other conditions could be when the write ahead log, when the write ahead log is full, then we flash to disk as well. So there are multiple conditions, but this is one of the conditions that indicates that the flashing operation should happen. So in this case, HBase is flashing the values to the disk, right? So what this means, as I've mentioned before, in this case, so HBase now is the client to HDFS, right? So basically, this is on a region server, if you can imagine. Then the client is co-located with the data node's process of HDFS. So this operation, so HBase is talking to HDFS via the API, flushing to disk very efficiently, right? So now we are flashing the value to disk, creating an HFile, right? And next we want to continue writing, right? And we write 2 values, 3 values, and now we're flashing to disk again, creating an HFile of the same size, right? And once we have 2 HFiles of the same size, what do we do? Is that these 2 HFiles are ready to be merged, right? But here we have another write operation. So some students have asked me, when to merge these 2 blocks, and what's the ordering between writing and merging. So the simplest answer is that they are separate and totally independent operations, right? But what HBase would do is that it will always try to prioritize the operation from the client as much as possible, because that's the critical path, right? So you don't want the client to wait just because you want to merge these two blocks. These are not critical. But if you are for example, if the write is happening in the middle of merging two blocks, then bad luck, because merging two blocks is quite I/O intensive, and this could affect the performance of writing. But typically, these are the two separate process, and this happens periodically. Okay, and what we have now is that we are writing another value, right? And then now here it comes to a read. We're having a key. As we have said before, we check everywhere. First, we check the mem store. If the mem store has the key the client is searching for, is asking for, then it will return immediately. Now we don't have, so we go to the mem store and check the indices somewhere in the memory as well, for each of the H files we are having. And now we have, okay, two key value pairs with the same key, and we return the one with the latest timestamp T4, and we return 109. Okay, so that's the latest value. Moving on, then we have the compaction, right? So there's no strict ordering, but at this point, we happen to have a compaction, for example, right? So what it will do is that we merge these two blocks together. And if you can recognize, you would say that, well, the merging process is basically, the merge part of a merge sort, right? Because we have a sorted list on both sides, and we can just merge this very efficiently, right? This is, this is a big complexity, very efficiently. And then what do we have? We have a delete operation, right? So the delete operation in this case, so it's a bit counterintuitive, right? So the delete operation in HBase is actually adding more items to our disk. So in this case, it's adding a delete tag to our mem store. So actually, it's called a tombstone. So a tombstone basically is a tag indicating that the client wanted to delete the key value pair with the key being Z. Okay, and if you can recall the formatting, so the last bit would be the type. So this is the type of the type. Oops, if I can spell, the type of the key value pair, and if the type is a tombstone, then that indicates a deletion operation, right? So previously what we're having is a Z in the memory. Because of the deletion, we immediately get rid of it from the memory, right? So if these tombstone were in the memory and or have been committed to disk, and if we were to have a Z key value pair somewhere here of some value, and during the compaction, we will delete this tombstone tag together with the Z key value pair. Okay, so the deletion only happens when the compaction happens. So they happen together, and that's also one of the reasons why we want to have the compaction, because I think you can imagine if we were not to have this compaction operations, then we will have lots of those tombstone tags cluttered in our cluster, and lots of Z values not being deleted. So during the compaction, we will delete the tombstones, and together with the values they are indicating to be deleted. Okay, that's the write operation. And then we can have another bunch of write, and we write to disk, creating another H file, and we are compacting again a series of writes operations, giving us two H files of the same size. And next we can compact these two H files to a single larger H file. right? And now we can even compact these two files to a larger file. So in that case, we make sure that we have an efficient data structure inside of our disk, and we can bound our seek time as well. Does that make sense? Any questions? No. Okay. Right. So that's all I wanted to cover. So let me check the solution. Right. I think I've covered all the grounds. And one thing I'd like to mention is that in this week, we also have a companion JSONic exercise notebook. So you are supposed to get yourself familiar with the syntax with arrays and objects, right? So you can nest arbitrarily different objects, a list in as you wish. And also we have the concept of sequence. Make sure that you understand what the sequence is. So the sequence is a flat structure, unlike array and objects. Okay, so they are always flat, one-dimensional, and you can create a sequence using various syntax. Oops, is a bit small. Let me zoom in. Yeah, and then also, get yourself familiar with this kind of syntax, how you can unpack an object, a list, an array, how you can unpack a sequence, okay? It's a very peculiar grammar, so the syntax is a bit different, at least to me, from what from the languages I'm used to work with. So yeah, please take a look, and I will be here. I will stick around for any questions you might have from the lectures, from the exercises, or for the HBase command line queries you might have for the first exercise questions. So if you have any problems, or just raise your hand or just hit me up or come to me, I will address your questions in this class. But that's it, guys. Thanks a lot.